Hi there! Welcome to the 5th episode of the Filters tutorial. Today we will talk about passive first-order high-pass filters, both RC and RL. And we will also introduce a more formal approach to the analysis of such filters, and any other as a matter of fact, which will allow us to determine how such circuits work when the frequency of the input signal changes. And finally, we will verify in lab that the findings of the formal approach actually reflect how these filters work in practice. Before getting into the details of this subject, please remember that the Team C's campaign is still in progress, and it will be until the very end of this year. Team C's has organized a fundraising to help clean the oceans of our planet, which are currently suffering from a lot of pollution, mainly because of the plastic we use every day that has found its way to the open waters. Team C's will devolve all the money collected to two charitable organizations, the Ocean Conservancy and the Ocean Cleanup, and they both pledged to remove from the rivers, beaches and oceans an amount of pounds of plastic and other garbage equal to the amount of dollars being donated. Our goal is to collect $30 million by the end of the year to remove 30 million pounds of garbage. Please look at the description below for the Team C's link where to make the donation. The oceans of the world will thank you. And now, let's begin. Hi there! I am Carlo Carrano, and this is Electronics Engineering Made Easy. In the past episodes of this series, we have seen the filters mostly from a practical perspective, and sometimes I have also approached them with some math to help figure out how we can design them. Today, since math can sometimes seem daunting, I will use the first-order passive high-pass filters as a way to provide more details on the math concepts used to analyze the filters, to make their use easier to understand. In short, my goal of today is to give you relatively simple tools to analyze any filter schematic you may encounter. To do that, we have to talk a little bit on dealing with passive components that change their behavior with the frequency, capacitor and inductors in particular, and how we can model them so that they can be used in circuit analysis like they were simple resistors. So let's start with the actual resistor, and then we will expand on capacitors and inductors. According to Ohm's law, if a current flows into a resistor, there will be a voltage at its leads that is proportional to the current itself through a proportional factor named resistance. The law is expressed with the equation V equals R times I. If we draw a diagram of the voltage with respect to the time, like for example a sine wave, because of that proportionality, the current will have an identical shape and position in time, although with a different amplitude. And whatever is the frequency of the sine wave, the resulting current will always follow exactly the shape of the voltage, and vice versa, of course. Let's examine now a capacitor of capacitance C, which depends on the ratio between the quantity of charge on the plates divided by the voltage at the plates. Because the capacitance depends on the voltage and on the charge, the correlation between the current, which we can assimilate to the movement of charges, and the voltage is not linear, but it depends on how the voltage changes over time. The correlation between voltage and current is therefore dependent on the derivative of the voltage through this formula. Let's now draw a diagram of the voltage as a function of time, similar to what we did for the resistor. And let's use one more time a sine wave to simplify things. Because of the correlation with the derivative, the current will not be aligned with the voltage, but will instead be shifted toward the left of 90 degrees. We say that the current leads the voltage of 90 degrees, or that the voltage lags the current of 90 degrees. Either way. Moreover, also because of the presence of the derivative, the amount of current will depend on how fast the voltage changes at the capacitor wires. And so we end up with a component that forces the voltage and the current values to depend on the frequency, not only the value of the component itself. This seems to be bad because the analysis of the circuit containing capacitors cannot be done without considering the frequency of the signals into the circuits, which wasn't necessary for the resistor. And now, let's take a look at the inductor. We know that the inductor stores energy in a magnetic field, which is directly proportional to the current flowing in the inductor. And we know that if the current changes its value, the inductor counteracts the change, generating a voltage meant to keep the current flowing at that same rate. Therefore, we can write that the voltage at the inductor leads is proportional to the inductance L and to the speed at which the flow of current changes. Because of that, the correlation between voltage and current is again through a derivative, this time of the current, as per this formula. If we draw a diagram of the voltage and the current with respect to time, we will see that the representation is similar to the one we encountered with the capacitor. This time, however, it will be the current that will lag the voltage of 90 degrees, which in turn will lead the current of the same amount. And now, as you surely now expect, because of the presence of the derivative, the ratio between the magnitude of the current and the magnitude of the voltage is not constant, but depends again on the frequency, like for the capacitor. And, like with the capacitor, this would again create trouble for circuit analysis when inductors are involved. To eliminate the issues of the simultaneous dependency on time and frequency, we make a good use of the mathematical studies of a great mathematician of the 19th century, Pierre-Simon Laplace. He created a method to convert a formula that contains derivatives in the time domain into a formula that is instead linear in the frequency domain. This method is called Laplace transform, and the procedure to prove the correlation requires a heavy usage of calculus. However, we can avoid the usage of calculus and specifically of the derivatives that we have seen appearing in the formulas for capacitors and inductors, and this we can do by simply using the results of the Laplace transform without going through all the calculations. And the result is that we can replace the derivative symbol with the letter S, which is a variable that contains within it the information of both the magnitude and the phase in the form of a complex variable. Don't bother about the term complex for now, it is just a name and does not necessarily reflect the complexity of the notion. We'll come back on that later, very briefly. For now, just note that we can use this variable S to replace the derivative symbol, and so we can rewrite the capacitor formula as I equals C times S times V, or SCV, and the derivative is gone. And similarly, we can do that with the inductor, obtaining the simpler formula V equals SLI. Note that the representation of the resistor formula does not change when we use the Laplace transform, because there is no derivative in it. And so after the transformation, the resistor maintains exactly the same formula, and the capacitor and inductor's formula can be rearranged to resemble the resistor formula like this. In here, we call the term 1 over Sc the capacitive reactance, which is equivalent to a resistance, but it depends on the frequency, and we indicate it as Xc. Similarly, for the inductor, we define the term inductive reactance as Xl equal Sl, which behaves like a resistor again, but in the frequency domain rather than the time domain. In other words, thanks to the Laplace transform, we can now study a circuit that contains capacitors and inductors exactly like they were all resistors. But instead of doing the analysis in the time domain, we do it in the frequency domain. And this is how the power of mathematics can actually simplify our life. Let's now take one little step back, since I promised you to talk more about the complex variable S. Let's do it now. You'll see that there is nothing really complicated about it. S is a complex variable just because it is represented with two terms. One that takes care of transients in the time domain, called the real part, and one that takes care of the dependency on the frequency, called the imaginary part. To distinguish the real part from the imaginary part, we add to it the letter J, which in this context represents the imaginary number 1. We don't have to worry too much about the mathematical meaning of the imaginary numbers. Just keep in mind that if you calculate the square value of j, we obtain the number -1. Yes, a negative number. Remember, this is a mathematical artifact that allow us to assign to a variable two meanings at the same time. It has a physical meaning only in this sense, and that is why it is called an imaginary number. The two parts of the variable s are called with the Greek letters sigma and omega. And yes, that's where the term omega, that we use so many times in electronics, comes from. Omega is an angular speed, or angular frequency, that allows us to measure time in terms of angles. We can translate such angular speed in frequency through the formula omega equals 2 pi f. F is the number of times we go around a circle at the omega speed in 1 second. The real part sigma of the variable s allows us to solve problems about responses to transients, like the response to a step, like in this diagram of voltage in terms of time. For a capacitor, we know that the response to such step is a current like this one. The inclination of the shape of this response depends on the sigma. But this is a discussion for another time, let's not put too much into this tutorial. Just know that when we don't care about the study of transients, but we concentrate only on the study of the steady state of the circuits in the frequency domain, we can remove the term sigma from the variable s and solve our formulas using only s equals j omega, which is an incredible simplification for the analysis of any circuit in steady state. Another important concept for the formal study of filters is the one of transfer function. Such concept comes directly from the one of the Laplace transform. Let's start by providing some basic information, and then we will use it to analyze some simple filter to try to understand its behavior before confirming it with some lab measurements. Please be patient and stay with me. Once we are done, you will see that it was worth the pain. Let's talk about a circuit as a black box. It will have an input, to which we apply a signal Vi, and it will have an output, from which we will take the signal Vo. This circuit can be done of a mix of any passive components, resistors, capacitors, and inductors. Now that we know that we can work with all these components, like they were all resistors, by using the Laplace transform, we can figure that we can find some sort of function h of s that creates a causal relation between the input and the output signals. We can even define this function as the ratio between the output signal and the input signal. The function h of s is defined as the transfer function of the circuit. And because we know that all the components in the circuit are linear in the frequency domain, we can assume that the transfer function can be expressed as the ratio of two polynomials, a numerator n of s and a denominator d of s. Recalling a few notions of algebra, we can also say that each of these polynomials can be written in terms of the product of a constant times the product of a number of binomials, where such number is the number of solutions of the polynomial equation itself. So, for the numerator, we can write it as follows. And we can write the denominator as follows. The bigger between the number of solutions n and m of the numerator and denominator defines the order of the transfer function. Yes, that's right, the order. That is actually the order of a filter when we represent it in terms of a transfer function, which you can now write in these terms. And we call the solutions of the numerator zeros of the transfer functions, while the solutions of the denominator are called poles of the transfer function. But what do we do with all this stuff? Let's clear the screen and just rewrite the transfer function in terms of its poles and zeros. In steady state, as we just learned, we can impose s equals to j omega. In such conditions, the function h of s becomes a function h of j omega, and we can write it again as such. This is a complex function. Remember, it is complex because it contains complex numbers, and not because it is complicated. Well, yeah, I know, it looks complicated, but please bear with me for a little more. Since this is a complex function, we can split its analysis in two parts, its magnitude and its phase, and analyze the two parts independently. The magnitude is basically the equivalent of the absolute value in the complex domain. The phase is the angle at a particular time on that circle we previously mentioned, where we travel at the omega speed. This angle is simply the arctangent of the ratio between the imaginary and the real parts of the transfer function. Yes, I am also using trigonometry now, but please be a little more patient. I had to say it to explain what we are doing, but that's about all I am saying about math. I'm really done now. I just needed to say that, because that is the reason why we can draw these two graphics, which I'm sure you have already seen somewhere, but you didn't know where they came from. These are the so-called Bode diagrams, from the name of the Bell Labs engineer that invented them about 90 years ago. From the first one, the magnitude diagram, we can see the behavior of a filter in terms of how it attenuates the signals depending on the frequency. From the second one, the phase diagram, we can identify the shift between the output signal and the input signal in a filter, depending again on the frequency. Do we need all the previous math to draw the Bode diagrams? No, at least not all of that. We just need some algebra to identify poles and zeros, and that's it. Once we do that, we can draw an approximation of the Bode diagrams with a simple graphical method, which I will now explain to you. Let's start by drawing the axis of a diagram where we can represent the magnitude of the transfer function as a function of omega. On the horizontal axis, we can identify the omega values for the zeros and poles, and we represent the poles with an X and the zeros with a circle, so it will be easier to know which one is which. Both the horizontal and vertical axes are represented logarithmically, so we can represent a wide range of values, which is important for analyzing filters and circuits in general. We start our diagram at the value for omega equals 0, which is right at the intersection with the vertical axis. The vertical coordinate in that point is represented by the logarithm of a, remember how the generic transfer function is defined, multiplied by 20, since we are talking about voltages. Why this number? This number represents the value of the transfer function for omega equals 0, expressed in decibels, which we represent with the symbol dB. For now, just keep in mind that the dB is a measure of the magnitude in logarithmic format. We'll get back to that in a moment. For now, please just accept it so I can finish describing how to draw a straight line approximation of the Bode diagram. Starting from the point on the vertical axis that we just identified, we start drawing a straight line until we reach the first point on the horizontal axis where there is a 0 or a pole. If there is a 0, we increase at that very point the slope of the straight line by 20 dB per decade. That means that when the frequency becomes 10 times higher, the line reaches a point 20 dB higher than it was before. Vice versa, if there is a pole, we decrease the slope by 20 dB per decade. And we continue to do so until we have used all the zeros and poles on the diagram. Note that if the slope was plus 20 dB and we encounter a pole, the new slope becomes 20 dB minus 20 dB, or 0, like in the case of this first pole in the diagram. And since the slope has become 0, the straight line becomes horizontal. And in this case you can see that after the first pole we encounter a second pole, and so the slope becomes minus 20 dB per decade, so it starts going down. You see, we were able to draw a representation of the magnitude diagram just by knowing the poles and the zeros without doing any further calculation. We can do now a similar thing for the phase diagram, similar and not identical just because the generation of the straight line diagram needs to be done by superposition of the individual diagrams for each zero and pole. First of all, we have to note that although the horizontal axis is still logarithmic, the vertical axis is not. We don't need a logarithmic vertical axis because the phases we have to deal with would always stay between plus and minus 180 degrees. And so the range is limited and we can use a linear scale for that. To make the drawing of the transfer function phase shifts, which are angles, we start again by drawing poles and zeros on the horizontal axis. And let's also draw some reference line for the angles. This time, at every zero, we have to consider a contribution of the transfer function such that the straight line in the range between 1/10 of the zero value and 10 times of the zero value goes from minus 45 degrees to plus 45 degrees. At every pole, we do the same, but this time we go in the opposite direction, from plus 45 degrees to minus 45 degrees. The rest of the transfer function is made by horizontal straight lines, and these are drawn accounting for the shift introduced at every zero and pole. This way, we obtain a straight line approximation of the phase diagram for each independent zero and pole without the need of any complicated calculation. To obtain the overall diagram, it is now a matter of adding up all the straight line approximations for each zero and pole. That can be done because we are working on a linear system since we are in the frequency domain and we are using the Laplace transform. And so, here are the three partial diagrams. The one for the zero is in orange, the one for the first pole is in purple, and the one for the second pole is in light blue. Adding up, we obtain an horizontal line at 45 degrees for the first interval. Then there is a straight line with a slope that brings it up to 135 degrees, then another horizontal line, and then we go down 45 degrees, then another horizontal line, then we go down again to minus 45 degrees, and finally another horizontal line at minus 45 degrees. Here, done. And now, as promised, let's clarify the concept of dB, or decibel. First of all, dB is 1/10 of a bell, which is the actual measurement unit. We tend to use dBs because the bell is a big number and we usually don't deal with big numbers. The bell is a measurement unit for the power in the logarithmic form. Moreover, it provides logarithmic value of the power with respect to a reference power. It is therefore a pure number without a real unit attached to it. Since the dB is 1/10 of a bell, to express the value of a power we need to multiply its value by 10 to obtain the number of dBs from the number of bells. This expression defines the whole concept. P is the power we have measured. P0 is the reference power from which we want to determine how much the measured power is different. And we extract the log from this ratio since we want to work with logarithms. And then, to obtain the dBs from the bells, we multiply by 10. But we said that dB is actually a pure number, so why stop at the power? The fact is that in electrical terms, the power is directly proportional to the square of the voltage, or to the square of the current, depending on what you are using, and as you can see from how we can calculate the power. And since we always consider a ratio, the constant of proportionality, the resistance in this case, goes away when we do the calculations. The result is that we obtain the same number of dBs whether we do the calculation using the power itself or the squared voltage or the squared current. Isn't that beautiful? We have the measurement of a magnitude that does not rely on the particular unit we are using, and also has a logarithmic value, so it is easy to represent large ranges on a diagram. The only thing is that we have to know what we are doing. When we use the power, we multiply the logarithm by 10, but when we use the voltage or current, we have a power of 2 within the logarithm, inside of it. Because of the way the logarithms work, this power of 2 can be removed from the exponent of the voltage or the current and can be put as a multiplier in front of the logarithm. And so, when dealing with voltages or currents, we end up multiplying the logarithms by 20 instead of 10. If we do this right, we can always obtain the right pure number representing the magnitude of the transfer function, regardless if we have found it doing the calculations with the voltages, or currents, or power. And the numbers will all be consistent with each other. And that's all you really need to know about dBs. And now that we have learned all that stuff on transfer functions and how to plot them with the method of the straight line approximation, let's apply our newfound knowledge on this circuit. let's assume we know nothing about it, and we want to understand how it works. Let's begin. So, this circuit has a series capacitor between the input and the output, and it also has a resistor in parallel with the output. Here is the input voltage, and here is the output voltage. If we look carefully, we recognize in this circuit a voltage divider. The input voltage causes a current through the capacitor and the resistor, and the current produces a voltage at the leads of the resistor, voltage that is smaller than the one on the input. We can therefore use Ohm's law and write the equation that allows us to find the output voltage when the input voltage is known. We will also write the equation in the frequency domain, using the capacitor as a linear component, thanks to the Laplace transform, which tells us that we can consider it like a resistor or value 1 over Sc. And so we write the following: output voltage equals to R over the sum of R and 1 over Rc times the input voltage. But look, now we have an expression where on the left we have the output voltage, and on the right we have the input voltage. We can readjust the equation moving the input voltage of the numerator in the right term to the denominator in the left term. And what we obtain? Well, the transfer function, of course. H of S equals to V out over V in equals to R over R plus 1 over Sc. We can rearrange this expression to change it in the ratio of two polynomials, n of s and d of s, by simply multiplying both numerator and denominator by sc. The result is src over src plus 1. Let's call now rc equals tau, which is a Greek letter, and since this tau now has the unit of second, we can define its inverse as omega c, the angular velocity we have seen in the theory we just learned. And of course, omega c equals 1 over Rc. Yes, tau is in fact the timing constant of the Rc circuit, and omega is something that resembles a cutoff frequency. But is it? Let's see. The transfer function numerator, src, has in fact 1, 0 at s equals 0. The denominator has one pole, s equals negative 1 over Rc. Now, in order to study the steady-state functionality of this circuit, we can just replace S with its imaginary part, as we learned earlier. And so we can impose S equals j omega, which in turn translates our 0 and pole into j omega equals 0 and j omega equals negative 1 over Rc. And if we take the magnitude of the two, we obtain omega equals 0 and omega equals 1 over Rc, which is omega c. And there we have them, 1 0 and 1 pole, that we can use to describe graphically how our circuit behaves at the change of the frequency by using the Bode diagrams. Let's start with the magnitude diagram. Let's draw the horizontal and the vertical axis, which describe respectively the values of omega and the transfer function magnitude. And now let's draw the position of the 0 and pole on the horizontal axis. We can now draw the first straight line starting at the position on the vertical axis. Since at the origin we have a 0, it means that we have to draw a line with a slope of 20 dB per decade, and this slope has to encounter the horizontal axis where we reach the pole, like this. Then, when we reach the pole, we have to subtract 20 dB per decade to the current slope. Since it was plus 20 dB per decade, now we have 20 minus 20 equals 0 dBs, and so the slope has become 0 and the next straight line must be a horizontal line. We will draw the horizontal line starting at the position of the pole, and we will continue drawing it toward the right, and it will go forever that way since there are no more poles or zeros. And now look at the shape of our transfer function magnitude. All the frequencies greater than omega c are unaffected. All the frequencies below omega c are affected with an attenuation of 20 dB per decade. High frequencies go through, low frequencies are attenuated. And so we can say that this is actually a high-pass filter. Since the highest power between poles and zeros is 1, we can also say that this is a high-pass filter of the first order, and that's how we really define a filter name and its order. Now you know, isn't that cool? Wait, there is more. We can make an even better approximation of the filter behavior. For that, you need to know that the straight lines we have drawn are actually the asymptotes of the real magnitude curve. Asymptotes are those lines that are tangent to the lines toward infinity, and therefore the actual magnitude curve is something like the orange line I am drawing now. This line encounters the omega c point at a value of minus 3 dBs, and so we define the cutoff frequency of a filter, that particular frequency where the magnitude of the signal is attenuated by 3 dBs. From now on, we will apply this definition to any kind of filter, whatever is its order and whatever is the kind of filter. We just need to do one more thing now. We need to see how the phase of the output voltage is changed with respect to the one of the input voltage. And for that, we can plot the second Bode diagram, the phase diagram, which we will also do using the straight line approximation. Let's therefore draw the axis for this new diagram. And remember, in the phase diagram, the horizontal axis is still logarithmic, so we can deal with large range of frequencies. But the vertical axis will not be logarithmic, because we only need to deal with angles that go at most between plus and minus 180 degrees. This is the location of omega c with respect to the previous diagram. And these points identify the position on the vertical axis of plus and minus 45 and 90 degrees. I am also going to draw these reference lines for later to make it easier to draw the diagram. These ones instead are the points on the horizontal axis at 1/10 of omega and 10 times omega. And let's identify omega c as the pole and add the 0 at the origin of the axis. Now, in green, let's draw the effect of the pole on the diagram. A line going from plus 45 to minus 45 degrees, starting on the 1/10 and terminating on 10 times the value of omega c. And then two horizontal lines at the two ends of the previous one. For the 0, since it happens at 0 degrees, the 1/10 and 10 times values coincide with the 0 itself, and so we draw only the right side of the diagram, which is basically a straight horizontal line at plus 45 degrees. The combined effect of the pole and the 0 is the line obtained by adding up the two separate effects. And so we start with a straight line centered at 90 degrees until we reach the point at 1/10 of omega c. Starting at 10 times omega c instead, we draw a straight line at 0 degrees. And then we go down with a straight line from plus 90 degrees to 0 degrees in the interval between 1/10 and 10 times the omega c. And there it is. This is the straight line approximation of the transfer function phase. And so we now know that the circuit we just analyzed is a high-pass filter with a cutoff frequency of omega equals 1 over RC and with a total phase shift that goes from 90 degrees to 0, centered at 45 degrees at the exact cutoff frequency. We can also say, since the phase shift is all positive, that the output magnitude leads the input magnitude of the signal. It is time now to verify that all we have done so far actually reflects the way the circuit works. Here is the setup for the experiment. I will be using an oscilloscope and a function generator. The output of the function generator goes to channel 2 of the oscilloscope, so we can see the input signal on it. The same output of the function generator, through a splitter, goes to a cable with two alligators at the other end, which we can use to inject the signal in the circuit under test. The other channel of the oscilloscope, channel 1, is connected instead to a probe, which we will connect to the output of the circuit, and so we can visualize the output signal of the circuit. This way, we will be able to compare the two signals. Here is the input signal on the oscilloscope. Let me zoom in so you can better see the details of it, and in particular its frequency and phase. And here is the circuit under test. we have a capacitor of 1 nanofarad in series between input and output, and a 1 megaohm resistor in parallel with the output, exactly as in the schematic of the circuit we have analyzed. With these component values, we should find an angular cutoff frequency of 1 over Rc equals 1000 radians per second, or a natural frequency of 159.2 Hz. Let's now measure the cutoff frequency and the phase shift to verify that the numbers provided by the theory correspond to reality. So far, we have an input signal with a frequency of 10 kHz. And if I move the input signal away, we can also see the output signal in yellow, which right now reflects the exact shape and magnitude of the input signal. And that confirms that at a frequency much higher than the cutoff frequency, there is no attenuation and no phase shift. Let's now put back the signals on top of each other. That way it will be easier to notice differences both in magnitude and in phase. Let's start lowering the frequency of the input signal to get closer to the cutoff frequency, and let's see what happens. Note that since I am lowering the frequency, I have to change the scale on the oscilloscope every now and then to be able to always see a few periods of the sine wave. So now we are at 2 kHz, 1 kHz, and we can already see that there is a slight change in the magnitude of the output signal as well as a phase shift toward the left. Let's reduce the frequency some more. Okay, now we are at 500 Hz, and now you can see a more pronounced reduction of the magnitude of the output signal, and the phase is definitely shifted toward the left. Let's go down now a little bit more with the frequency. Now, before we go too low with the frequency, let's use the cursors of the oscilloscope to have a more precise measurement of the difference between the input and the output signal magnitudes. In particular, we want to identify the frequency where we have an attenuation of the output signal of 3 dB, which is equivalent to a delta V of 0.707 volts. That frequency will be the cutoff frequency. So we need to set the cursors to measure voltage on the channel 1, which is the output signal. The start cursor is aligned with the top of the input sine wave, and the end cursor needs to go down with a delta V of 0.707, which we can read on the bottom right of the oscilloscope screen. Well, unfortunately it looks like I am not able to set the exact value. The closest value I can obtain seems to be 0.720. Well, we have to do with that, and we will have to remember that we will have an approximation of the cutoff frequency read caused by the slightly wrong position of the end cursor. So now let's lower the frequency some more until we touch with the yellow sine wave the end cursor. Here, this should be it. The frequency reading is of 190 Hz, close to the value of 159 we calculated. This is expected since we measured with a delta V greater than the one it was supposed to be. Let's now measure the phase shift at the cutoff frequency. To do that, I am going to move the sine waves so that the input signal crosses the origin of the axis at its node. To measure the shift, we need to know how many degrees each notch on the horizontal axis represents. We know that half sine wave is 180 degrees. And we can count in the same interval 16 notches. Here. This means that each notch represents 11.25 degrees. Let's now count of how many notches the yellow signal, the output, is shifted toward the left. And I count 4 notches. So now, multiplying 4 by 11.25, we obtain the actual shift, which is 45 degrees, exactly the phase shift we expected. So yes, the measurements confirm the theory, but we already were sure about that, right? Let's now take a look at another circuit and let's repeat the same process. The theory first, to identify the type of circuit, and the measurements second, to prove the veracity of the theory. We will analyze this circuit, where this time we have a resistor in series with input and output, and an inductor in parallel with the output. So let's draw here the new circuit now. The resistor, and then the inductor. Here is the input voltage, and here is the output voltage. Now, if you compare this circuit with the RC circuit we analyzed before, you'll see that this one too is a voltage divider, and so we can write the VO as a function of VI in this form. As a result, the transfer function of this circuit, given by the ratio of VO over VI, can be written as SL over the sum of R and SL. And then, dividing both numerator and denominator by L, we obtain S over R over L plus S. In here we can identify the angular frequency omega c as R over L. This transfer function, like the previous, has one zero and one pole. The zero is for S equals 0. The pole is for S equals minus R over L. Substituting S with j omega to analyze the steady state of the circuit, we have a 0 for j omega equals 0 and a pole for j omega equals minus R over L. Now we extract the magnitude for both, obtaining omega equals 0 and omega equals R over L, which is omega c. At this point we can draw the Bode diagrams for both the magnitude and the phase, with the same procedure we used for the RC circuit. And this is the final result. Notice how these diagrams are basically identical to the ones for the RC circuit. The only difference is the way the cutoff frequency has been calculated, since the components are different, but the kind of circuit is the same, another passive first-order high-pass filter. Let's now run the same measurements as for the first circuit, so we can verify that the theory works as well for inductors and capacitors. The setup is the same, but the circuit is different. This time we have this resistor 10 kΩ and this inductor of 10 mH. Input and output are connected as before. The cutoff frequency in Hz can be calculated from omega c in the same way we did for the RC circuit, and for that we get a cutoff frequency of 159.2 kHz this time. Let's check if the measurements support this number and the phase number of 45 degrees at the cutoff frequency. This time we start from a frequency of about 300 kHz, well above the assumed cutoff frequency. You can see that the input in yellow and the output in blue almost coincide. So let's start lowering the frequency, and let's keep the cursor on with the same setup as before. We can already see that at 160 kHz the attenuation is already well visible, as well as the phase shift toward the left. Let's lower the frequency more. And now the output wave seems to be at the right attenuation, so the cutoff frequency seems to be about 135 kHz. A little lower than the one we calculated, but remember that we are approximating because we cannot identify the exact value of the delta V at the cursors. Actually, to compensate for that, I should have probably stopped when the sine wave was touching the end cursor from the above to have a more precise result, and that would have given us a slightly higher value of the frequency. Let's now measure the shift. This time it looks like we have 23 notches for 180 degrees, which gives us 7.8 degrees per notch. The yellow wave is 6 notches to the left, and so it is leading by 7.8 times 6 equals 45.9 degrees, which is a result very close to the 45 degrees we expected. In conclusion, today we have learned the formal approach to the analysis of filters and other types of circuits that modify an input signal in some way. We have also seen how to apply the methodology to first-order high-pass filters, and we also confirmed in lab that the theory is sound and provides valid results. In the next episode of this series, we will see how to apply the same methodology to more complicated filters. Thank you for following this video till the end, and please share in the comments if this video was useful to you and how. And now, please don't forget to give me a thumb up, and also subscribe to the channel if you haven't done so already, so you will be informed of all new videos I will publish in the future. Finally, don't forget to stop by the Team Seas website to make your donation to help clean up the oceans. And maybe donate also to this channel to help me make more videos for you to watch. All the links are in the video description below. See you in the next video, and as usual, happy experiments!